Okay, so now coming to the diode current equation, so we will try to find the diode current for the forward bias condition and the reverse bias condition. Now this PN junction diode will be formed of the P-type semiconductor and the N-type semiconductor. In the previous lecture, we have obtained the derivation of the barrier potential, and this is the barrier potential. We can see that because when you join this P-type and the N-type semiconductor, the charge particles, or you can say the charges which are around this PN junction, they will try to diffuse, and due to diffusion, the electron hole pair will be recombined. The electron will recombine with the hole, and they will get vanished, and because of that, a layer will be formed which will be depleted of all the charge carriers. So now you can see that in this region there will not be any charge particle. Can you see the charge particle here? No. So now there will be only the acceptor atom and the donor atom. Now these atoms are immovable. They will remain at their place only. They will not move. This now in the p-type semiconductor, the majority charge particles are holes only, and the minority charge particles are electron. Now similarly, coming to the n side, or you can say the n-type, the majority charge particles are electrons and the minority particles are holes. So now in the previous lecture, what we have assumed that the charge concentration of holes on the p side will be pp. Now this will be in they are majority in number, and here now suppose we can say this as 1 lakh atoms, or you can say 10 lakh atom. Now this will be in thousands. So we'll assume this as pp. Now this will be p number of holes in the n side. Just a minute, I'll write it again. Number of holes in the p and the n side. So you can see there will be a vast difference in the concentration from p side to the n side. So I think in the previous class we have obtained the relation as Vb will be equals to Pt natural log of Pp. Now suppose if you want to find the value of Pp, then how you will find that will be, this will be Vb will be equals to Vt natural log of Pp upon Pn. This is the barrier potential. Now if you just rearrange the equation, you will be able to find Vb upon Vt will be equals to natural log of Pp upon Pn. Then Pp will be equals to, I think this will be natural log. If you just move this here, so you will be able to find what? You will be able to find the exponential, that is Pn exponential of Vb upon Vt. You just take the exponential on both the side. So I think this will come above the exponential, and this natural log and exponential will get cancelled. So Pp upon Pn. Now you shift Pn here, so you will be able to find this equation. Okay, so now this will be in the no bias condition. Now this equation is valid. This equation is valid for the no bias condition because there will be a depletion layer. This equation will be valid for no bias condition because we have not applied any external voltage to it. Now what is going to happen if you apply the voltage to it? Now there will be two types of biasing, or biasing you can say. There will be a forward biasing and the reverse biasing. Now suppose we will have the forward biasing. We will apply the external supply, or you can say the power in terms of battery. Now so you can see here, this is the p side, and if we have connected the p-type semiconductor to the positive terminal of a battery and n-type connected to the negative terminal of a battery, then the diode is said to be in the forward bias condition, and in that case the diode will have to act, I will have to operate as a switch, or you can say that is the on switch. So for that to happen, you will have to remove this depletion layer, or you will have to deplete, or you will have to break the depletion layer. So I think the current will only flow when there will be a breakdown of this depletion layer. But how will you break this depletion layer? Just by applying the biasing, and that too in the forward direction. Now what is forward direction? P type to the positive terminal and N type to a negative terminal. So what is going to happen when you are applying a voltage? There will be a formation of external electrical field. I think this is the internal electrical field which has been formed due to diffusion, and this will be formed due to the application of the voltage. So you can see that there will be the external electrical field. This is E external and this one will be E internal. So you can say that E external and E internal, they both are opposing each other. You can see E internal is from this to this and E external will be from you can see the positive terminal of a battery to the negative terminal of a battery. So what is going to happen? Now this will be apply more pressure onto the depletion layer. This will apply, there will be a repulsion. There will be a force of repulsion between positive and the majority particle. Now in this case the majority particles are holes only. So there will be a force of repulsion and there will be a force of attraction between the opposite charges. Obviously like charges repel each other and unlike charges attract each other. So there will be a force of repulsion and the force of attraction at the same time. So the majority charge particles will try to drift towards the depletion layer and they will try to pierce, they will try to enter into this depletion layer. So what is going to happen now? When suppose this hole is traveling, you can see that this hole is traveling. We'll take this hole is traveling, and suppose if it has entered into the N-type semiconductor. Initially that hole was in majority, now it has come into the minority side. Fine, now it has come to the minority side, so there will be an appreciable change. Now even if one hole will enter into the N-type, there will not be any significant decrease in the holes in the P-type. But you can say for the N-type. Now suppose if you inject or if you just put the hole into the N, because already the holes are minority in the N-type. Now let us say that okay, I'll try to explain using some numbers. Now suppose we are having 100 holes here and you are having 5 holes in the N-type, because holes are majority in the P-type and minority in the N-type. So 105. Now suppose one hole will enter into the N-type because of the application of the voltage, then the electrical field, there will be a force. So because of that, this value 100 minus 1, that will be 99, and here you will be having 5 plus 1 will be 6. So you can see there will be a significant increase in the concentration of holes in the N-type, but you can't say the same about the concentration of holes in the N side. Or in the P side, sorry, the concentration of holes in the P side. The 99 is equals to 100. Fine. So in that case, what we can say that due to the application of the electrical or you can say the voltage or the electrical field, the concentration PP will remain constant. You can see the depletion layer decreases further. Depletion layer decreases further. Can see the holes are coming here, the holes are coming into the depletion layer, and because of that the depletion layer decreases further. You can see that. So from the second figure you will be able to find the change. Initially the depletion layer was from this point to this point, but now due to the application of voltage there will be an electrical field, there will be electrical force, and because of that there will be a force of repulsion and force of attraction. Because of the force of repulsion, these holes will try to enter into the depletion layer. So what you can see that the depletion layer decreases. The depletion layer decreases. Okay, so distance of the width of depletion layer decreases. Initially it was from this point to this point. So now we can reduce the the width also, that is this is minus xpo dash and minus x and o dash. Okay, so now what is the voltage which is applied across the depletion layer? So you can see that the barrier potential has decreased. Initially it was VB when there was no voltage. Now due to the application of the voltage, that is the applied voltage VD, the resultant voltage will be VB minus VD. Fine, VB minus VD. Okay, depletion layer width decreases, at the same time the barrier potential also decreases. Okay, so now we can write two equations based on this. We can write two equations based on this. This one is for the no bias condition. This equation is for the no, when nothing has been applied, when no external voltage has been applied, or you can say for the no bias condition. Now this equation will be written for the bias condition, that to a forward bias condition, because you can see that because of the application of a voltage, there will be electrical field, there will be a force of repulsion, though these holes will try to pierce into the depletion layer, and because of that the width of the depletion layer decreases, and at the same time the barrier potential also decreases. So what will be the new value? So this will be okay, so PP plus Pn plus delta B. So we can see that the charge concentration will remain same. Fine, because 99 were there, no, and there will be 5 plus 1 6 were there. So Pn plus delta P, this much holes have traveled into the n type, and because of that there will be a significant improvement, or you can say significant increase in the concentration of the holes in the n side. Fine, so now you just divide these two equation. Okay, so when you divide these two equation, what is going to happen? PP upon LHS and LHS will get divided, RHS and RHS will get divided, so you will come across this Pn plus delta P, so you will be having delta P, this equation. Just have to note this equation. Now we have talked about the holes of the holes which is there in the p-type semiconductor. Now similarly you can write for the electrons in the n-type semiconductor. Okay, now what is now you can see that when this hole has diffused into the n-type semiconductor, you can see this much type of the relation. You can see the concentration decreases, the whole concentration decreases. When electron will try to move from n-type to the p-type, you will be having this type of relation. There will be a decrease in this slope. I think we have discussed in the barrier potential. So you can see that what is the concentration? You can see this one will be delta n e to the power of minus x upon ln. You can see the downward slope is there, and because of that we have taken e to the power of minus x upon ln. This is the diffusion length. Fine, this is the diffusion length we have written. So I think suppose if you want to write, because for delta p xn, so what we can write? Okay, so this will be, so suppose one hole has traveled, we can write one hole has traveled into the n type, one hole has traveled into the n side. Fine, so what we can write, the density, this is the charge density delta pxn. What we can write? We are talking about one hole, so this one will be delta p. Fine, e to the power of minus x. So where it has traveled into the n side, so we will have to write xn, and this is the diffusion length of the hole. Fine, this should not be ln. ln means what? Diffusion length of the electron. What has traveled? Hole has traveled. Where it has traveled? It has traveled into the n type. So that's why we have written e to the power of minus xn upon lp. Now similarly, now I think this equation you have obtained, delta p is already calculated. So from this equation you will have to just substitute the value, and after substituting I think you have got this equation number 4. So now what is the current density? Now what is the current? Because ultimately what is happening, the majority charge carriers are diffusing. No, majority charge carriers are diffusing. So that's why we will have to take the current density due to the diffusion. So we have taken jpxn. Okay, so already this is discussed, that will be a negative minus q dp upon dx. You just have to refer the barrier potential video, and then you will be able to find this. Okay, so now dp upon dx, so this is the concentration of holes in the n side. So p will be replaced by this delta p xn. Okay, so now put the entire value in this equation, and now you will have to do the derivation of it. Now this will be the derivation, you will have to do it. So okay, so now coming here, what minus qp, so I think this holes in the okay, so pn, this will be the concentration of holes in the inside. This will be a constant value. So I think e to the power of vt minus 1, because we are differentiating with respect to xn only. We are differentiating with respect to the xn only. So this entire term will be treated as a constant value. This entire term will be treated as a constant value. Now here e to the power of x minus xn upon lp. So how you are going to differentiate? Okay, so just I think I will come here, dxn e to the power of minus xn upon lp. So you can see here minus xn upon lp, this minus 1 upon lp is a constant value. So I think we will write like this only, and e to the power of minus xn upon lp. So what is the differentiation of this? This one will be this value. Okay, so now I think everything will be crystal clear. Okay, so e to the power of, okay, so now coming here, okay, so minus q into minus, so I think minus minus will get plus, so we will be having this equation. Okay, so now this is the current density. We want the current due to the hole which has diffused into the n-type semiconductor, because ultimately if you want the current to flow, then you will have to flow the majority charge particle which are holes in the p side into the n-type. We want our holes to move into the n-type. That's why we will have to find the current due to the diffusion. So ip, I will be equal to what? J into a. J will be equal to I upon a. No, J will be equals to I upon a. Just have to put the value. So I think this a term, it is the area of cross section of the p-n junction diode. This will come here. So this will be IPXN. Now similarly you can write for the current due to the electrons which has traveled into where, I think in the p type. Yeah, not I think, it will travel into the p type only. So this one will be you will have to just replace all the symbols. This xn1 will become xp, lp will become ln. So this is okay. So now I think this xn and the xn, now when you apply the forward biasing, so what is going to happen? Slowly and steadily the depletion layer will decrease to a zero value. Fine, because you can say that there will be more force of repulsion, and this there will be more force of repulsion if you just increase the value of Vd, and when this Vd value will be equal to the barrier potential, when Vd value will be equal to the barrier potential, then what is going to happen? When Vb will be equals to Vd, so when Vb will be equal to Vd, then the resultant voltage which is applied across the depletion layer will be zero. So that time the current will flow heavily from P towards the N side. So I think you will have to put Xn will be equal to 0 and Xp will be equal to 0. So when you put Xn will be equal to 0, e to the power of 0 will be equals to 1, e to the power of 0 will be equals to 1. You will be having these two equations. Okay. So now something is common here. I think UA is common. So this is the dP upon LP Pn. This is also common. You can take it outside. Okay, these are the only things which are not common, so that's why we have taken in this way. Okay, so now I will be equal to I0 e to the power of Vd upon Vt minus 1. So I think you can say this charge is constant, area is constant, and everything. This much part is a constant value. You can say this much part is a constant value. So you can replace the entire thing by a constant, and that will be a reverse saturation current. Okay. So this is I will be equal to I0 e to the power of Vd upon Vt minus 1. So I think we will be able to find this diode current equation. So in the next lecture we will try to plot the PI characteristics of the PN junction diode. Thanks a lot for patience listening.